Hello. Hopefully I'm coming through loud and clear. Awesome. Hello. Good morning, Doogie1379. Can you hear me? Awesome. That's excellent. My name is JF. I'm VP of Sales and Marketing. And shortly, Carlos Espina, who's our CTO, co-founder as well, is going to go and join us. Let me flip over so you can see me. Ta-da! Here I am. And yeah, we're going to be basically printing some stuff. I'm going to be showing you some things that I've been making the past few days. I wanted to go over kind of a little bit how we print, what kind of specifications you can do with you can hit with SV2, and the kind of kind of things you can actually make. Right now, I am just finishing a print. I'm actually, if you can see in the video at the bottom, that's the first of 2 layers with the vias, those black dots. Those are the vias that I just printed. I'm going to re-upload the files and sort of lead you through the processes that I did on a software side to explain how I actually got to the point that you can see on the camera right there. By the way, do you think, is the feed okay? We share a space with a large number of other hardware companies, and I'm never 100% sure if the quality is 100%, but I am also recording it locally onto my drive, so a higher quality feed will come up later, so you can see everything clearly. What I might just do is just open up the floor to any questions that might come up right now that I could probably sort of address, because there's 2 things I want to do. I want to show you some examples of stuff we've made. I want to show you how the software works. And then finally, I want to actually print the top layer and cure it so that you can see the machine operating. So we have a live chat going right now, so hit us up with questions right there, and I can answer any questions you have. In the meanwhile, I'm just going to lead you through some photographs that I took recently and put together. So we've been printing quite a bit. We've gotten some excellent new ink, and we've been actually playing with a lot, being able to do many things that we weren't able to do with Squink. If you take a look at this is an example of some things I made yesterday and the day before. So these are all 2-layer boards. All of the traces are, some of them are 8 mil, some of them are 10 mil. A few of the bigger power lines on the board, the biggest board you see there, not the panelized one, it's anywhere from 8 to 10 to 15. Those components are QFPs and SOICs with SMT connectors. So the whole thing, and it's the board you see in front of you is called a BotDuino. It's a design that I developed. It's based off Arduino. We're using a Mega 328 EU, I believe. And the board on the right you see there, this is all coming through, is actually a panelized design that I have as well, and it's a sound meter essentially, and it consists of things like an AT Tiny 85, numerous LEDs, capacitors, resistors, so forth. Aha! Hello, Carlos. So Carlos just walked into the door. Yeah, man, I haven't seen you anywhere. And let's get to the next photograph. So here's an example of what I was talking about. So that's a close-up of something I assembled. Those are all components that are all glued down. That one microphone was soldered on, and basically you connect it and it turns off. It's supposed to detect sound. This design here is a 4-layer board I made last night. You may recognize the design from earlier photographs, and essentially it is a 4-layer board with each layer representing the different layers. Yes? Yeah, you can. You can't see it? I'm consulting with my man in the room. Can you see it? Is it live? Yeah, it's coming through.
Yes.
Can you hear the volume?
Yeah.
Yeah, okay. So according to the live chat, we were okay too, so. So that's a 4-layer board. And that's basically sort of just an exemplar of what we can do in terms of printing. And the process we go through, we will show you shortly. And I wanted to get to one more photograph, and this is a panelized design, 10-layer board. I don't think you've actually even seen this yet, Carlos.
Cool.
Yeah. By the way, do you want an earbud so you can listen in? Okay, so you are now mic'd. Please tell me if anyone can hear Carlos as well.
Hello?
Can anyone hear Carlos? Okay. Hopefully. Excellent. All right.
All good.
So yeah, that's an example of sort of a different design you can do. I mean, where I basically just like panelized it out. And how the hell we do this? That's a really good question. And that's why Carlos is here, to explain how we actually print these examples I just showed.
Okay. So good morning.
Yeah.
I would like to walk you a little bit through the process that we follow, but I would like to take one step back.
Do you want to sit over here and we can switch over to video?
Yes.
Okay. So I'm handing this over to Carlos. You can have a seat right here.
Part of the reason, or kind of a bit of story of how we got to the current process, is that we began by analyzing the different types of technologies that you can use to print or lay ink on a substrate, right?
Yeah.
So when you talk about printing, you have different types, right? You have gravure, and you have like photolithography, and you have inkjet printing, and you have extrusion of ink on substrates, right? And one of the things that we did try for some of our early years was trying to extrude ink onto substrates. From the beginning, creating multi-layer prints was one of our main concerns, because we know that it is really hard to achieve like complex circuitry without having multiple layers, especially when you're talking about 2-hand or high-density chips. So when we were trying this extrusion mechanism, we realized that we were getting a bunch of bumpy traces, right? And you were trying to escalate layers by creating, say, overpasses with insulating layers on the cross points. You would very quickly end up with an elevation that would make it really, really hard to attach components to it, and essentially will also create these discontinuities in your lines that would also affect your signal. So after doing several tests with different things, we ended up using inkjet. Inkjet is a very proven technology. It allows you to create very clean features, very small. You can easily scale to higher resolutions if you have the right head. And there's another thing that is quite interesting, and is that the fact that inkjet is more controllable, right? Like you can to a certain point, since the dots that you're laying down are so small, you can either do redundancy passing to make sure that you cover the area, guaranteeing that you are covering like opens, for example. You can control the thickness of your deposition by doing multiple passes, knowing and calculating the volume that you're placing. So those are things that inkjet allows you to easily control. And after playing with it for a little bit, we came up with an interesting question, which is, I don't know if anyone in the public is aware of, but when you're talking printing, you always have two options to approach let's say the question of how do you print, right? And there's two main technologies. One is a thermal inkjet, right, by which in other times it was known as bubble jet. What you do is you heat up a chamber where you have liquid, which is ink, and as you heat it up, it will create a bubble that eventually will burst and will propel the ink out of the head through an orifice that's essentially your nozzle, right? And then you have a second type of technology called piezoelectric technology, in which you have walls that vibrate, right? It's essentially crystal walls, piezoelectric, and they move, and as they move, they compress the ink, jetting out the ink, right? There's a lot of things said about one or other types of inkjet printing. I guess the most important thing to keep in mind is that thermal relies on heat to push your inks out. As of inkjet, piezoelectric doesn't have an issue with it. So if your material, the one you're printing, is sensitive to thermal energy in some way, let's say you're using an ink that can cure at very low temperature, you probably don't want to use a thermal head. In our case, we actually chose to go with thermal because when you compare the pricing between thermal and piezoelectric of the head, I'm talking about the specific head, the cost of a thermal head is minimal. So when I say minimal, I mean, it comes down when you're doing mass production, as like I don't know, for example, HP Boss or Lexmark used to do back in the day. Those heads were like cents per head. When you're talking piezo head, the process that they require to be developed and manufactured is way more expensive and is more involved, which is why the piezo heads tend to be more more costly, and these actually turns into a kind of a problem for us because we have a printer which, in the end, yes, the main purpose of it is printing circuitry, but we keep testing new types of inks. So we have inks for insulating layers, we have inks for conductive layers, we have inks for carbon printing if you want to do capacitive printing, for example. We are trying a dissolvable ink, right? And every time you're trying a new ink, you're going to run into head clogs, right? You're going to damage your head multiple times. And if you're doing this on a process that is based on piezoelectric, you are going to, drain your funds very quickly. So essentially what I want to put in your head is the technology that BotFactory uses has a long thought process on why we chose what we're using right now. What we use as thermal head, it allows us to try different types of inks. If you are into ink experimenting, we can offer you empty cartridges that you can use to try new inks. They are very reliable. When they fail, which is usually at the end of their lifetime, throwing them to the garbage doesn't mean that you're throwing away $1,000 or $2,000, right? It's a head that is meant to be disposed, and the inks have been tested to work well on the thermal stresses as they are put into or put through when they are being printed, right? When they are printed. Okay, so now specifically about the way we print things, right?
Mm-hmm.
When you're talking multi-layers, there's mainly 3 steps or mainly 3 parts of the process. The first one is laying down I'm going to break it into 3 parts. One is laying down the conductive ink, and when you do that, essentially you are trying to achieve very consistent thickness all around the print. You are trying to do multiple passes to make sure that, so inkjet printing, it is not rare that sometimes one nozzle will take a little bit longer to start firing than another because it depends on the state of the nozzle and the state of the chamber. So we do multiple passes to cover different nozzles to make sure that we have high reliability.
Yeah, and just to insert my own notes. So I just showed, right now you can see pictures of a print we're doing right now, the big one in the middle. And the smoothness is kind of seen in the reflection. That took about, I would say, to cover, 2 by 3 inches, that took about 25 to 30 minutes to cover. It's continuously passing over. And how big is the printhead? It's like half an inch?
Yes, no, it's half an inch.
It's half an inch with 300 nozzles, thereabouts. So I think we use half of them. And how much ink is it per? It's like 10 picoliters.
Yes, 12 picoliters.
12 picoliters.
Yeah.
So, and I mean, that might not be more than like 0.5 or 0.10 milliliters in the end of ink over a very thin area, but selectively deposited. But the critical thing is getting it smooth, because the conductive ink has to essentially.
It has to be smooth to make sure that your signals travel effortlessly, and they don't create noise.
Yeah, you can see in this photograph, for example, you can see sort of the slight striations, but the striations are
yes.
I mean.
So those striations that you see on the green mask or the insulating layer, those are technically property of the insulating layer. Like conductive layer doesn't behave exactly the same way as insulating does. As of like smoothness and like high conductivity and making sure that the lines are shaped properly in conductive is kind of the most important thing. In insulating, it's about keeping thickness constant and making sure that there are no bodies or mountains. So you just want to keep a very flat surface, which is kind of the most important thing. You would see, like if you look at this picture, you can actually see very, very small lines horizontally, right? When you measure those lines, they are sub 10 microns. That is very, very, very small. The difference. It's a difference that is very easy to pass when you are printing with the conductive thing that we are using right now.
Yeah, we get a lot of questions about smoothness, and a lot of the work was actually put into making sure that not only the jets were jetting constantly, because they need to jet over a long period of time. And I think these are the kind of heads that they use on like large scale industrial printing, right? Like where there's high reliability, high functionality.
The heads that we're using are usually you can find them like in plants where you are printing, for example, boxes, or where you print barcodes. And it's essentially used for industrial printing. Usually they have large arrays of these heads printing continuously. Yeah,
but I mean, in the end, it doesn't actually impact the sort of fine tuning of the traces and so forth. I mean, for us, it's kind of, I guess, a real concern is like piezo systems are like single head. I think from piezo companies go for like as much as $1,000. I mean, the high quality ones.
Right?
Yeah.
I mean, I know there are ones that are a little bit less expensive because they are also meant to be disposable. But then the system that uses them can easily run you above like $60K per printer, right?
Yeah.
The typical cost of a standalone head can be between, I don't know, $500 for the simplest model. If you have something that's a little bit more complicated that can give you better resolution and stuff, you can easily run it for $4,000 or $5,000.
Cool. So it's cured with a UV lamp, right? So the UV lamp. Oh, let me flip over to that part. So there's a UV lamp right here. You can see it on the middle photograph. So you can see sort of a set of mirrors. There's a UV lamp there. So it's curing it with you don't see it there on your computer. You see it here. But basically, it's essentially curing the material as we print, right?
So as I was saying, like the first part is curing. It's printing conductive layers.
Yeah.
Conductive layers are printed with conductive inks. It's a process where we essentially slice what you give us to print. It's a Gerber file. It's a picture. We can actually print essentially BMP like bitmaps, right? We can print them as well. So if you have like a drawing and you're not much of an engineer, you want to do more of an artistic thing, you can also do it. So we slice it and we spread like or distribute the firing, synchronized firing, and then we use that to create the representation on the substrate. Once we have printed things, we cure it. We cure it using heat. So our inks are heat activated. You will go through a process of curing at around 140 C for 5 to 10 minutes. That depends on the size or the area that you're printing. And then after that, we move on to printing the insulating layer, which is what you were saying, right? And in the insulating layer, we change heads to the insulating head where UV light will do most of the work for curing. And then it's a high power UV light. As you are printing, it will be essentially pinned and cured make sure that it doesn't move, it doesn't close your vias.
Yeah.
Like that.
The major difference between Squink, which some of our people on there might be familiar with, and SV2, the concept is the same. We're printing conductive and insulating layers, but the hardware improvements we've made are fairly significant. Along the heat bed thing, there's a fan now, so it can heat and cool. We go from 0 to 160 in a minute, and then cool it down in 2 minutes, which is just, it's insane. For me personally, as just a side user, it's like you print your board extremely rapidly, and allows you to do things like a 4-layer board. I'm calculating a 2x4 inch board. That's 4x4. Sorry, it's four layers to be done in 2 hours. To take a 2-layer board in Squink, it took me 2 or 3 hours.
Yes. Because
it was equivalent size, because the print head was smaller, the heat bed was not so great, and critically, the UV lamp was also a lot poorer. So SV2 has a proper set of UV LEDs, right? UV LEDs.
High power.
You can speak to the safety of these things, right? There's a big yellow sticker. But it's not dangerous.
It's UV light, but it's not in the range where looking at it will make you blind. It's powerful. Obviously, you shouldn't look at it directly. That's kind of a disclaimer.
Yep.
Not look directly into the UV light, but clearly the reflection will not.
Okay. Someone is asking a question from our viewing audience. What does this say?
What is the cost of an active cartridge? And is the ink, are they refillable? Simulation of weight of copper is possible. Okay. So cost.
Yeah. So to answer your question, William, the cost of a cartridge of insulating and conductive ink, the total cost of the supply package that comes with FR4 and 2 cartridges is $700. And each cartridge themselves is $300. If you cost of ink, if they're refillable, they're not refillable. The reason we're not making them refillable right now because the inks are exclusive to us, and the cartridges are very very hard to find. Right.
But I'm going to give additional one more piece of information there. Every time you print with particles, which is what we're technically doing, right? You are accelerating particles out of the nozzle. So the more you use the cartridge, you will start eroding the edge of that nozzle. So if you keep using it, let's say forever, right, or for long periods of time, more than the ink that you have put in there, you will start getting bad results, right? Because your nozzles are eroding. As I said, the cost of the cartridge is minimal compared to the cost of the ink at this point. So pretty much there's no point in keeping the cartridge. You can always try to refill. We're not gonna stop you if you do that. You just keep in mind that having a new cartridge is not gonna cost you a lot of money, but indeed it's going to help you print better.
Yeah.
Because of the erosion.
Yeah. So we fill up. We've been doing some sort of hardcore testing where we're printing a lot of boards, and I think that there's a reasonable possibility of printing anywhere from 30 to 50 of these guys, which is this board right here. I've been doing some basic calculations, and 30 to 50 out of these is about reasonable, which means that each board is around $5 to $10. $5 to $10 for, what is this, 2 by 3 inches? How much do you think you'd have to pay for a board that's 2 to 3 inches, so that's 6 square inches?
Yeah.
And you get it in a day. In a day? No, this took me 50 minutes to make, by the way. 50 minutes. I timed it. 50 minutes to make a 2-layer board. With a mask, okay, that was an extra 10 minutes. But
yeah. So I think the main, you when it comes to cost analysis, you are gaining in time, and the cost of one board. Technically you're paying for a single board instead of paying for 4 or 6, which is what a standard manufacturer will ask you. I would like to move on to the simulation of weight of copper because
yeah, that's a great question. That's a really interesting question.
So essentially, you can control how thick your layers are when you are during the printing process. There's a question that tells you essentially how many layers or passes you want to do. The more passes you get or you would do, the thicker it will be. You also have to keep in mind pretty much the same way that you do with like a standard manufactured boards. The thicker you print, the wider your traces, your minimum trace width is, right? And so essentially, you can't expect to have a, I'm going to say something crazy, like let's say you can't expect a 5 mil line if you are having a 4 ounces copper thickness, right? So, I mean, essentially, the higher you go, the thicker your traces will be, and in this case, it applies exactly the same. But it's completely doable, and it's up to the person that is printing.
Yeah. Okay.
Now we have some tables where we talk about width of lines and amount of current that they can transport. We don't sell this as a tool that will replace like a high power. So I'm thinking like, I don't know, 60 plus amps going through like or line, like, because this is ink, right? So it's gonna be thinner. But we have tested this before, and we have, I believe, I'm thinking a 60 mil line, and we're pushing something like 10 amps through it. No problem. Like,
yeah, we made a power supply. I mean, with Squink, where we were using different inks, or actually different ink processes. Yeah, it's the resistivity on a sheet resistance goes down as low as I believe 30. I've seen. We have to do proper tests. 30 milliohms, which for an equivalent amount of half-ounce copper, I believe the thinnest foil you can get. I don't think they make quarter-ounce copper.
Yeah,
do
they do.
They do?
Yeah.
Okay. Well, I know what the figure is for half an ounce. It's about an ohm, or a 1 milliohm per square.
Mm-hmm.
But I mean that's pretty low. But I mean like 30 milliohms is within striking range for most applications.
Yep.
Where you're doing things like digital signaling, everything up to like high power, where you're pushing amps like no problem at all.
Just to verify, so 750 for print package, yes, and if you're just buying the cartridge, it will be
300 each. Yeah, print package comes with FR4 and Kapton, so we can print on materials like that. Are there any other questions? Because I think at this point we want to move on to. I'm just going to literally walk through the process of printing, and then close it. So if anyone wants to ask any questions for Carlos,
yeah, I'll be here. I think maybe we can start the process.
Yeah, no. What I'm gonna go through is the process, the actual software. So I'm already halfway through a print, but if I re-upload the files, I can just skip all the steps, right? And go to the last layer. Yeah, okay.
So another thing that's important to know or to keep in mind is the fact that when you are printing the insulating layer, you are also defining the drill files that are going to connect different layers.
Yeah.
So essentially, if you're printing a 2-layer file or board, you will require at least 1 drill file.
Mm-hmm.
If you're going to use 3 layers or 4 layers, then you need 1 drill file in between layers, unless you're using the same file for all of them, right? So when you have like perfectly true via, which is what most people do most of the time. But if you wanted to do blind vias, then you definitely need to have like a different drill file in between each layer, and that is completely transparent. It doesn't.
Okay.
Yeah.
All right. Well, I'm gonna go skip to this next step where I'm just gonna make sure I'm gonna widen this whole thing so you can see the beautiful process that is our software package, designed mostly by Carlos. Now, this is kind of the fun bit for us because I kind of consider our software to be kind of our like key, I guess you'd call it like sort of our key, the keystone. Because anyone can print, inkjet print, but like the fact that we're processing everything on a machine right here, we're using a browser-based interface, and there's no manual, which scares a few people. But I'm going to explain to you why this is kind of, I guess, the logic behind the software. I mean, you designed it, so you probably explain it better. But I'm just going to walk through the process of how I got to the step I was at, where I was literally about to print the last layer. So first off, I'm connected to the machine using a local network. Actually, no, I'm directly Ethernet, but you can use a local network. It's the same process. Essentially, what's going on here is I have opened up essentially my browser, and I'm playing with our our flagship dev unit, dev1.local. It's essentially one of our machines. And I put it into an address bar of an ordinary browser. I'm using Chrome on a MacBook, but you got a Dell, I think, or Acer?
Yeah.
It's a Windows PC. It doesn't really matter. Linux, we have people using Ubuntu. It doesn't matter. As long as you have a browser connection to a network or direct Ethernet line, you just have to provide SV2 an IP address so that you can connect to it. All the processing that you're about to see is happening on the machine. It's not happening on the local network or the computer that I'm using. So the advantage is if you're in a space like an office where multiple people are using it, you can all upload files from your own computer rather than having to put it onto an SD card, walk over, do a MakerBot style, things like that.
There's an additional important advantage of this. We publish software updates very frequently, and we have a single point of update. So essentially, every time we upload or update our algorithms to print, more defined, or to print a little bit faster, or to increase the number of footprints that we have on the library for pick and place, all those updates go to a centralized point, which is the onboard computer of the printer, so you don't have to worry about people updating their software every single time or installing new software every time you change your computer. So it's like a self-contained unit.
And I know a few people who work in the defense industry are reeling at this possibility of having an internet connection on a device. There is an option now with SV2 where you can get a USB key that contains the updates, and essentially you plug it into the machine, and then you update from the USB key. So we got a lot of complaints. Well, we got a few people who were like, I can't buy this because, national security will not allow it. But we're, private companies. I mean, we understand that a lot of people buy SV2 or Squink for reasons like, I want to do everything in-house, partly because it's not just faster, but it's also more secure. Think twice before sending your design out to China. They might copy your product. So let's start. What I did is I click on Start New Print, and then the machine is going to ask me how many files essentially I'm going to upload. And it's slowly uploading. Okay, so I can do a single layer, or I can do 2-layer. We're going to update that to 4. Yeah, but essentially what it's going to ask me for, and this is the thing that confuses a lot of people, there's no single file design for circuit boards. There's no SDL. There's Gerber files, though, and SV2 takes Gerber files. We do not require you to use our special software and formats. No, we take standard Gerber files, and we can also take JPEGs, TIFFs, bitmaps, anything that's is it a bitmap file? Bitmap file. Okay. So in this case, I used Upverter to design this particular design, but everyone I know has used everything from Altium. We've had people use KiCad or KiCad, depending on where you are. And all you really need is a couple things. For example, the outline file. The outline file is just the mechanical edge cuts or the mechanical details. But you could use.
That tells you where the border of the board is.
Yeah, and you could just technically re-upload the trace files, but you might want to have spacing around your traces. Otherwise, the machine will just willy-nilly cut stuff off, because it's basically going to look from the bottom left corner to the top left corner and then create a size file. So if I'm confusing you and you're using this machine, there's a helpful little help button where it explains exactly what you need to do. I'm not sure if this is showing up in my feed. Is it? Okay, excellent. Okay, so you can see it. Yes. So what's going on here is it explains exactly what I just said. Next step is the bottom copper, and yeah, that's kind of blatantly obvious, bottom copper, but you could use the top copper, you could use the layer 2, you could use anything. SV2 is, I mean, the software is kind of open to taking anything. You could upload a mix of files, probably, like an image file and Gerber files. It's not really dependent upon.
Yeah, I wouldn't recommend that, because then aligning them may be tricky.
Yeah. I'm working off a single design that I worked. The next step is the drill file, and this is a little complex. The drill file has to be the plated drill file first. Plated drill file. Yeah. So if you also click on the helpful little help button, it tells you exactly what we're looking for. .brl, .gerber drill file. Excellion files work. I mean, really, it's just anything with dots. It won't work if they're X's or if they're circles or triangles or text. They have to be actual, what is it, vector images?
Is the image, like, it's something that represents the image of where the drills are going with the correct size of the hole. Right?
Yeah.
In the end, you can click on it to zoom in. So
oh,
see
yeah.
what we're looking for, right?
Yeah.
What we're looking for is something like that.
Yeah. Yeah, it might show up as a text image if you look at it, or text file if you look at it.
The file may be text.
Yeah.
So what I'm trying to say is that so what is representing with the text should be done like that.
Yeah.
It shouldn't be, because you may find some drill files that have like different icons to show different sizes of holes. So you will use like a square for a 30 mil hole and a triangle for a 50 mil hole and all that, right? So we actually want to see the circle. Yeah.
So while you're talking, I also uploaded the top layer, and it's exactly like the bottom layer. It's just the Gerber file with everything, including my sort of traces and my pads and all that jazz. Here's something that's a really common misnomer. You don't have to flip the board to print. Some people think this is a double-sided board. None of these designs, and I really wish I had an example, are double-sided. Hopefully in the future, we'll figure out a way to actually tell you how to do this, or maybe we could just print the whole thing where the substrate and the circuit is all in one thing, and you just peel it off something, and there you go, you have a two-sided board. For now, these are sort of multi-layer one-sided boards. The bottom and top copper are just words that people use to describe essentially I am building a board. For us, it's really just the bottom, the first layer, second layer, third, fourth, fifth, so on and so forth. So yeah, you can't really do two-sided boards. And when you're designing a board, you should keep that in mind. If you have components in your bottom copper that you need to attach somehow, you have to move them to the top and reroute everything. What are a couple of things that maybe, oh yes, the thing about drill file is also that when we print, we kind of do an expansion. So you may want to space off your vias more than you might want to. And what is the typical rule for vias, do you think? We go down as far as...
No, it's the same constraint that we have for lines. So,
okay.
Yeah, so that shouldn't be
yeah.
a worry.
The vias shouldn't be smaller than 8 mils or 10 mils.
Yeah, I mean, it's actually the same for when you're manufacturing, right?
Oh, okay.
You should want to make sure you give room for the drill. In this case, it's the same, so I would say try to go for maybe a 15 mil via. 15
mil, yeah. So the examples I was showing earlier, they were all, typically I would just double the width for the via size. So, and believe it or not, I printed a design, because I am the ignorant one in the team. I don't have an electrical engineering degree. So I kind of just do things willy-nilly, probably to the frustration of half the people here. The funny thing is I was printing stuff, and I realized that I was actually violating, my vias were so close, they were within 10 mils of each other. I was able to print them because I wasn't beating the rule in regards to my machine, but I was totally violating at least advanced circuits rule on getting on drill points being farther. They should be farther than 10 mils or something, or the diameter of the trace, or the diameter of the drill. That's because you're drilling stuff with traditional manufacturing. So, the cool thing is that you can do some things that you really can't do with traditional manufacturing. Where things may matter. Space is super valuable in a lot of industries, so this is one thing that's kind of interesting. Before we move on, any questions? I'm keeping a John's eye on. No, I haven't seen anything. Okay, good.
Keeping an eye.
All right, so what's happening next is the machine's going to process everything. This handy little icon indicates what? Basically, it's working. Yeah, as I said before, everything's happening on board the machine. One thing that's really awesome about SV2 is that it's got a way more powerful processor than our Squink. What are the specs of this guy? It's like a...
It's a quad core. It's running at 2 gigahertz, I think, compared to a single core at 1.
Yeah. Okay, so for all you computer nerds out there, and I'm sure some of you are, that means it's powerful. Why can't I? Oh, that's why. Oh, do it here?
Yeah.
Oh, okay, there you go. I figure I know how to do this. Ta-da, here it is. So that is the final process board. And so I can toggle with the eye icon the various parts. It's not going to print the outline, by the way. It's going to look probably like this. The outline just defines the edges. Bottom copper is going to happen first. I mean, I can literally explain what's going to happen. It's going to print this. It's going to print the drill file, which is, if I toggle everything here, you can see it's printing the inverse of the drill file. It's an anti-drill file now. This is the most confusing thing about how 3D print electronics is that we're not doing any drilling. We're taking your drill files, though, and we're inverting them.
We're creating holes.
Yeah, we're creating holes. If you think about it in the craziest possible way. That's a cool, and that's kind of what allows us to do fun things like printing on flexible substrates, where drilling is not really an option. The final step is vias, and that's the point at which I got to with the machine. And then the vias are essentially just filled with copper, and that's how we do the interconnects. So people ask us, how do you do multi-layer board without drilling or any of this? Is we print the bottom layer, we fill in everything except for the holes, fill that with copper, or silver rather, and then we print the top layer, and that's how we interconnect everything. I'm making a video, by the way, that's going to show how we printed everything, not just this, but like a similar design. So keep your eyes open on your emails. I'm probably going to be sending that out this week. Okay, so it's asking me to insert the cartridge, but this doesn't matter right now because we're just kind of skipping past the processes we've already done. But it's going to ask me to attach the head. This is no ordinary dumb head. This is a head that actually has quite a lot of computing power on the back of it. It's its own computer, essentially, processing all the firing, because we have quite literally 300 nozzles that we have to fire at a rate of some absurd speed.
Yeah.
It's not easy. So, and in fact, when we do updates, we often update the head separately. And by the way, do you know that we can pick a place to dispense? We will be talking about that in future webinars. And it's the same deal. Like, there's some hardcore processing going on in each one of these heads, primarily because that's the best way we can get the kind of quality we need. So, what I just passed by, and I should have gone over, well, I'll see it again. That slider just simply controls the number of layers that I can sort of do passes. I am just rapidly just skipping over stuff, but typically I would just start printing, and then go from there. And then it would print, stop, cure, and then it would ask me to detach the head, where I would probably replace the cartridge with a new head. So the head with the cartridge in there with another cartridge, the insulating layer. There's this wonderful set of instructions telling you how to take care of your cartridge. Cartridge care is important. The insulating ink does not require refrigeration. The conductive ink, it's useful to keep it in the fridge. It lasts longer. I keep it in the fridge. It's generally a good rule, but if you leave it out for a fortnight, it's not a big deal. And there's these clips that you put on. Oh, is my video feed going? But yeah, you'll see it. You can see them in the photographs. Okay, so this is what we're talking about when you don't really need a manual. I mean, as we say, the machine is the manual. It tells you what to do at each step and kind of helps you understand what needs to happen. I'm just going to change the video a little so you can see what's going on. You might be able to see. No. There's only so much room. Yes, I did. Yeah. No, I've gotten to the via step basically.
So this is a screen that is very directly related to the copper weight, right? So here is where you define how many print repetitions you want. You can go as thick as you want, or actually, like the minimum recommendation is what is the minimum working, right? We usually actually go for 2. You can go less, you can go higher, depending on how thick you want.
I use slightly different settings, and there's a long story behind that, but it's programmed right now to 2, but I think I found something better, and we'll probably talk about this after, because I've been printing a bunch. I haven't backed you up on, I haven't updated you on things I did. Small things. So next step, we go to, okay, so we're going to build, yes, okay, so it's going to ask me to print the insulating. Yeah, so it's printing the drill file, and then it's going to take, forever to print the drill file. And once we're done that, yet again, asks me to detach the head, which I do. And then once it detaches, the machine's like, aha, we'll move on to the next step. And it will ask me to put this cartridge to sleep, which is, in this case, put it in the drawer. The conductive ink is the only one you should consider refrigerating. And then we put the conductive ink cartridge in, attach the head, and the machine will essentially detach the head. Okay. All right. So I've already done the via printing. So I'm going to skip that. All right. So we're at configure print settings. We've made some changes. You only need one now. So we'll go to the next step. I'm going to take a moment to essentially and basically start printing. And then I'm just going to switch quickly over to the video so that we can see in all of its glory the printing process. Yeah, give me take 1 second. All right, so I know the video may or may not be like 100% clear. I'm watching very carefully on the chat line to. Oh my God! You kidding me? Looking good. No. Look at that. There we go. Okay. Right now, Carlos and I are looking with bated breath, a birth of a new top layer of copper, well, silver, off of the top of this trace. Looking good so far. Probably my major concern is those pads, and everything looks pretty good. By the way, this is an excellent opportunity for people to ask questions. If you have any questions, please feel free to hit us up. By the way, there's 12 people watching. If you guys are already users, make yourself heard. If you aren't, I would really want to know what brought you here. I know a few people here based on your usernames, I think from previous conversations I've had with you. You guys are interested in SV2. Where's everyone calling from? Mostly UK. We have one UK guy. I'm not sure where Richard Thomas and Doogie are from, but we are in New York, and we are now more than open to take live demos. If you want to come by and hang out and print with abandon with the team, come on by. Well, not print with abandon, but like you can hang out. We can print something with you and really get you excited about having an SV2.
Yeah, I guess one of the most exciting things about having a printer like this is that you don't have to wait to see your idea come to fruition, right? Like,
yeah.
It actually served as when we were trying to develop, or we were starting to develop SV2, where we wanted or needed a new power source, and it was a thing that we realized very quickly. Like we got our new prototype, which we technically manufactured because we thought it was ready for prime time. And as soon as we connected it, we realized that the power sources were a little bit underpowered. So we had to design a new power source, and it's like design took us, I don't know, whatever the equivalent of 2 hours or whatever takes you to make sure you have all your components and the BOM is complete and all that. Printing and building it took, an hour or so. It was very quick, and it's definitely something that made me very happy.
Yeah. Well, I think you designed a lot of the boards on SV2 to be printable with SV2, right?
Yep.
So that's one of the things we want to do is do some direct comparisons. Oh, wow. So Relgard is from Erie, Pennsylvania. Okay. Greetings. Richard Thomas is from New Philadelphia, Ohio. So old Philadelphia wasn't working out, I guess. I mean, hey, we're talking. I believe one of the people here who signed up was from York University. I've never been to York, but one of these days I should really go check it out because I'm from the old York. I mean, would that mean New York? Whatever happens if someone makes a town called New York? I don't know. How does it know how to place components? That's a really good question. It's magic. This is patented magic? No. Good question. You upload the centroid and rotation files, which are typically exported from EDA file with XY coordinates. Lol. So they export them from your EDA tools and with the footprints and the X and Y coordinates.
We're going to be doing a webinar covering pick and place as well, right?
Yeah. Yeah. So you should definitely sign up, Richard. That will be coming up.
But kind of the interesting thing is to say that if you are, maybe you're not, but if you're familiar with any pick and place machine, the process it's relatively similar in the sense that you use these center rotation files. It essentially says or tells the machine for each ref dash, right, each reference designator, where that part goes and what rotation it has, assuming that you've placed it in zero rotation on the tray.
Yeah.
And once you define that, then the machine will take it from there pretty much. Like
exactly. Yeah. So you may have seen some earlier. Yeah, no, I removed the head. That was me.
Oh yeah.
I just those fans get annoying after a while. Well, I'm also concerned about whether or not our loyal live chatters or live webinar rights. How would you call someone who goes to attend the webinar attendees can hear us? By the way, to update you on the current situation, the machine is currently curing. So it takes about 7 minutes to cure a single layer. So if you do the math, and I mean, since we started printing, it's been about, what, 10 minutes? Maybe 8 minutes? That's less than that.
Yeah.
That's fast. I mean, people say, okay, why don't I just buy a milling machine? Let's actually just do some direct comparisons. Milling is, unfortunately, what's the word for it? It is subject to the tyranny of its own, it's hung by its own petard. It has to mill over the entire design. So the more complex your design gets, the more milling that has to happen. More points of failure because as the lines get thinner, you have a chance of breaking off the trays. Inkjetting doesn't have that issue because it's literally just passing over. So one of the main advantages of 3D printing over subtractive technologies, additive over subtractive, is that complexity is free. Like you can do extremely complex designs and have a high reliability or a high chance of like complete success. Succeed. And even if you do fail because of a design fault or whatever, you can just reprint again because the cost of a loss is very low because it's so fast. So, I mean, I have examples even with Squink, but now it's even faster with SV2 where I've gone through 4 or 5 iterations before I was happy, and then I went on. And, you know, we do cost comparisons with milling. If you're doing very basic boards, you know, they're okay, but you can't move on that. And then there's the added benefit of the fact that we can do things like, because there's no tooling, we're not touching the substrate, there's no need or problems with printing on flex materials or other exotic materials, like we've printed on ceramics, we've printed on plastics, like other plastics. Like our polymer is a very common type of, it's a unique acrylic. You can print on acrylics, other plastics, PTE, PNN, which is a very common flex material, all these kind of things. Yeah, you're trying to, yeah, you see the problem, right? But that's kind of the major advantage. When you compare it to something like dispensing, which is commonly found with companies like Volterra, Voxlite uses dispensing, although I don't think they sell their machines anymore. There's a company called Nscript that does dispensing. We consider dispensing, but yeah, you take it away from me. You know why we didn't do dispensing?
Yeah,
for trace building that. By the way, the machine can dispense onto pads, but we don't dispense the traces, and there's a reason why.
Yeah, I mean, it's pretty much what I was saying at the beginning, right? It's a matter of keeping flatness so you can guarantee continuous progression on layers. So if your first layer is bumpy, the second layer is going to be twice as bumpy, the third layer is going to be 3 times as bumpy, and so on. So it has a ceiling that is reached really quickly if you don't keep your flatness. In addition to that, and that's actually another thing, it's important to note that we do extrude, but that is a different class, I guess. We're in a webinar. So we have a head that can do extrusion for you if extrusion is your kind of thing. Although we don't recommend it for compact boards. And yeah, so you always have options.
I'm going to see, the printing's almost done, and I'm thinking I could take a photograph and I might be able to actually upload it here. No, it doesn't allow me to upload stuff.
We're having a technical difficulty because the camera that was aiming at us seems to be not working.
Yeah, you can, but I can actually see it here. Just there's about a delay of God knows how long. But that's okay, because I think the print's going to be done in, what, a moment now? Let's take a look. Where's my...
I mean, technically, we could do this, right?
Oh, hold on. Take a look. We could just...
So for printing is done at this point, and JF is going to demonstrate a couple of lines for you.
Yeah, I'm just waiting for the video to show up. Yeah, okay, it's going to come shortly.
Okay.
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 That's fine.
Have to take one of the lines on the left.
Yeah, I can do this. Right. So you can probably hear this. That is the multimeter, and this is a complex design, but I think this is the ground. Yep. So that's the longest trace.
Right. You have to try it on the other side of the
board. Yeah. No, I know. That's what I'm doing right now. I know, but it's a delay. You'll see shortly. Okay. What you're hearing right now is not a dead patient. That is actually indeed the longest trace on my. Hey, I designed this. I know where the traces are. That's the ground line going to the to the ground pin on the USB. So that is the longest trace, and that trace is my sort of go-to hardest trace to do. It comes up and down from top to bottom at least 3 or 4 times. What's the image here? 18. Yeah. That's highly reasonable. So that passes through, I think 6 vias. It passes through many times. That's like the ground line.
What is the thickness of these lines? What is
10 mils. Everything's 10 mils. There's a bunch of 8s where I needed because it's the QFN. It's not QFN, QFE. It gets really crazy around the short everything. Yeah, it's high density, right?
And you can't do high density if you have a single layer. That is just impossible.
I think I spaced everything 10 mils wherever I could, and then went to yeah. Do you want to take it out? Okay.
Yeah.
Yeah.
So we can actually use this.
So I just wonder if I can sort of focus. Yeah. Unfortunately, I cannot look at my live screening app, but you guys can tell me if that's any good. Looks pretty good to me on at least on my fingers.
It takes a little bit to focus, so you just leave it there for a little bit. I think that's good.
Yeah. Well, we're gonna send photographs of everything done. What? You want to look at me?
Yeah. So we're going to use this camera so we can.
Aha. Okay. So you can see. Oh yeah. There you go. So you can see it right now. Yeah. There's the live footage. You know, it doesn't. It's okay. It's okay. What we're going to be doing, have a seat.
Yep.
What we're going to be doing is we're going to be sending everyone here a copy of the photographs that I showed you earlier. I'll show you a photograph of what we finished printing, yeah, link to the permanent link of the actual video, which is going to be the same one as the one you're watching right now. You guys probably have a lot of questions, and feel free to share everything you see here. I'd love it if you guys had any questions. You can contact me at contact@BotFactory on our forum on our website. SV2 is available for sale, by the way. We're selling it right now for $16K. We're going to be doing some little bit of goodies to the end of anyone who buys it by the end of the year, including things like free river press shears and some consumables. You'll be hearing about that this week. Yeah, but I mean, if you guys have any questions, please feel free to contact us.
We, by the way, like challenges, or actually, it's as you know, like circuit printing or electronics printing is kind of a nascent, technology. So if you have questions on something that you may want to do, but you're not absolutely sure it would be doable, oftentimes a demonstration is all it takes to figure it out. Like at least we try it. And on the other hand, we are usually capable of doing a lot more things that you imagine that we can. That's historically how it's been. So if you have any interesting challenge that you want to pose, please reach out and we'll be happy to help.
Right on. All right. Thanks, guys. Talk to you soon.
Thank you.
Bye-bye. Ah.